of voltage between them. And so the question is, how much charge must be put on the plates to produce this voltage difference? So now that sounds like a pretty strange thing, but I thought about it for a while, and why do they use the word capacity? Where did that come from? It's another word that sometimes uses a condenser. Condenser, I'm not so sure where it came from, but capacity, I could finally figure out what was in the minds of the people, I think, when they came up with that word. Electrical capacitor is most easily represented by two plates, one of which has plus and one of which has minus on it. You have an electric field between them. You attach it to a battery, and what will happen is that, say, the plus charges, if you want to think of it that way, want to get to the negative charges, they feel that there's a negative guy somewhere over here, so they run over here and they charge up this plate. At the same time, if you want negative guys would run here, or else you might say that if there's positive we're talking about, positive guys would run away and you get an equal balance of positive and negative thing, and then what will happen in a case like this is an open circuit, the current will stop flowing. What happens when you charge a capacitor, you attach it to a voltage source, the charge goes, and when the voltage here builds up equal to the EMF that you start with, when the V equals the EMF, there's no reason for it to go anymore. See, when this has no charge on it, the pluses will run, but pretty soon, plus is running out of here, say, oh, there's already pluses there, I don't want to go there. And it settles down to where this capacitor picks up the voltage of the EMF. So what happens is that if you plot the current, what you really have to do is put a resistor in here to make things act well. The current is going to start at some height, and let's say you have a switch in here, which I will show you in a minute. The current starts, and over a long time, eventually, it's going to go to zero. This is when I close the switch here at t equals 0. So this is the current through the whole circuit. The current goes through the resistor. I might put an ammeter in this circuit here, and I could put a voltmeter across here to measure the voltage on this capacitor. The current will current will flow, but eventually this will charge up, and once this is the same as this, the voltage around the circuit is 0, and this current will stop. There'll be no current anymore. And what happens, the voltage on the capacitor will start out at 0, because there's no charge. The voltage on the capacitor is, I always start out with C equals Q over V. So V is equal to Q over C. So what's going to happen is that the voltage is equal to Q over C. So as the charge gets on the plate, the voltage builds up on the plate. So the voltage on the plate is going to do something like this, to rise up to a voltage equal to Q over C, which will be the voltage of the EMF. So that's how capacitors work. Okay. The current at first will be all the voltage across the resistor. So that the current here at the beginning is going to be the EMF over the value of that resistor. That's going to be the initial current up here, because what happens is that the current runs through here. Fast changes run through a capacitor, and the current will be running through this resistor. So that's how it basically looks. This is the I. Now the I on the capacitor is actually equal also to the I in the resistor by continuity of current. Whatever flows through here flows through here. So those are the same. But the voltage on the capacitor is that. Okay, just for fun, let's put down the voltage on the resistor. Anybody want to guess what that is? It's the voltage on the resistor is I times V equals IR, R of the resistor. Now here's the current, so the voltage should track with that. So it should do something like this, right? Because at the beginning, a lot of current flows through this capacitor, and in the long term, there's an open circuit. The current goes to 0. There's no voltage drop on the resistor. Okay, this is in your book, I think, but I want to move on. I wanted to give you. I thought out why capacity? Why capacity? What does it have to do with capacity? And funny thing I figured out. I think some people have mentioned this as an analogy, but it's an analogy to a tank of water. A tank of water with a certain area and a certain height of water. So what is the quantity of water in this tank? It's the area times the height. Okay, now I have a capacitor. Let me put it this way just to make it a little more similar. And I use the definition of capacitor, V equals Q over C, or whatever. The other way would be, well, let me give it one other term here, just multiplying across, Q equals V, or C times V. C times V. Same, right, formula? Okay, so here the quantity of charge on this is equal to C times V. So here I think is the analogy. The quantity that's inside a tank is equal to a geometrical factor, the area, times the height of water you put in. The quantity of charge on a capacitor is the capacity. That's a geometrical factor, as you'll see. It just depends on geometry, times depending on the voltage you put on. So the voltage is analogous to the height that you put in, and the capacity is analogous to the area of the tank. So that's my feeling for what capacity is. And actually, this analogy will work very well. You can derive all the formulas for capacity based on a tank of water of a certain height or voltage and a certain capacity for the area. So that's the quantity. So the analogous features are the area resembles this, and the height is analogous to the voltage. In many ways, yeah. Okay. So we have. So we can go on. This is what a parallel plate capacitor does. You just charge it up and you develop an electric field between the plates, and we can derive what the capacity is. You can figure out what the electric field is between the plates by the amount of charge on the plates, And then you can get the voltage, and you can plug into the formula, and you get the, I don't want to do this now because it takes time, and you can do it yourself, actually. It's not hard. And we may get back to it a little bit. It's a very nice application of Gauss's law to get this. But what you end up with is for a parallel plate condenser, or capacitor, what this capacity ends up being for parallel plates is the area by the separation. So the capacitor is epsilon naught A over D. Again, it's a geometrical factor, just like the area of the tank is a geometrical factor. It just depends on the geometry, and this constant here from electrostatics. There's one other slight complication. If you put some stuff in here, some dielectric material, you would then modify this by putting in a factor of K to represent some dielectric material in there. I don't want to go into that either at this point, but I'll mention it a little bit later on. So the idea is that the capacitance is a storage thing. You store charge in it. Once you charge it up, you can store charge in it. And as I say, the analogy with water is like the area of a tank. It could be unlimited height, but you fill it up at your will to a certain height. Capacitance is a certain geometrical thing. You can put as much charge on it as you want, depending on the voltage you apply. And here are a bunch of different style capacitors. These demonstrate the area factor very well. See, there's a fixed plate, and the relative area of this plate with respect to this is variable, so that I can vary the capacitor. In very old radios, you could dial your radio, and inside the radio was something like this. This goes back to the 30s. This was the kind of capacitor they used. More to the point nowadays, you'll see things like this, which when you take them apart, what they are is two metal sheets separated by an insulator. So that's kind of like, you see, this is two metal sheets separated by an insulator. But you want to get a lot of area, so you make the paper or the insulator thin, and you have the metal coating, and then, so that's the trick. There's another little guy here, and then there's this giant one over here. Shall we do that one? Oh, let me not do that one yet. Let me do something even simpler. Namely, one of the uses of the capacitor, because it depends on the separation of the plates, it's area over separation, you can make what's called a condenser microphone. When you do music, you ever use microphones? Called a condenser or capacitive microphone. And the idea is very simply this. When sound, you have a capacitor, the blue things there. One of the sides is rigid. It's called the back plate. That's rigid. And then you have a diaphragm in front. When sound wave comes in, it pushes on the diaphragm. And it changes the spacing between the diaphragm and the rigid one, which changes the capacitance. So and then you put a battery in there, connect it to a resistor. And in order to maintain the battery voltage across that circuit, some charge must flow to and from the capacitor. And you measure, and that current flowing through the resistor produces a change in voltage, which you then put in an amplifier, and then you send it on its way, and you've got a microphone. You've converted sound waves into electrical fluctuations on a resistor, which you then send down, and that's your condenser. I suppose these are very good. They were the standard in recording industry. It's not the only way to make a microphone, but this is a very nice way and a beautiful application of a thing. The other one that I like is trackpad. Now this is an interesting one. The idea is, do I have my, yeah, here it is. See, I can move this around by moving my finger. You guys can't see it. Maybe you can see it. Okay, I'll try to do it this way. I don't want to lose it. Oh, don't want to lose it. Oh, here we go. Okay, and that's a very clever gadget, right? I mean, remember the old days, there'd be a ball or something, track ball, or else mouse things, but why does it disappear? Where is it gone? Ah, came back somehow. Okay, the way this thing actually works is there are capacitors underneath here. When you bring your finger near here, it draws off some of the charge in that local area, and it tells the computer where your finger is. So the trick is, this is the patent. This is from a patent disclosure where the guy draws how it changes the electric field in this capacitor. And they point out that if you can't draw off the current, it shouldn't work. So I'm going to put on a glove and see if I can, what happened to the thing? It seems to disappear when I go away from it for some reason. Come on, guy, come. There you go. All right, there you go. See, with the glove, it doesn't work because it can't draw off the current. It doesn't even know I'm here. Come back, come back. Can you see that? Okay, see, with this finger, with this one, it doesn't do anything. So I can imagine somebody working in a cold place puts on his glove. Oh, my computer is broken. I can't track anymore. But I tried various things, and some insulators work and some don't. For example, paper doesn't work. Let me see here. See, with paper, maybe you can figure this out. But I've tried all kinds of stuff. Some things work. It gets through paper. I don't know why. It doesn't get through cloth, I think. Where'd it go? Here you go. See, it doesn't get through cloth. But it doesn't. Now, this I just picked up on the way walking here. I found this on the ground. It's a miracle. Let's see. Oh, well, it should, because, it's metallic conduction, so it should work. So that works. But on the other hand, when I tried this wire, it didn't work. See that one? It does. Although I would have thought that I could conduct through here, but it doesn't work. I don't know why. Cotton doesn't work. Plastic is interesting. It goes through plastic. I don't know why. If you can figure this out, good for you. And I picked up a leaf. Now, this is a dry leaf. That dry leaf doesn't work. Then I picked up I had a fresh leaf. I thought maybe the moisture in the leaf. Ah, here. This I just picked. Oh, that doesn't work too well either. That's a freshly picked leaf. I picked it right outside the building here. Okay, so the beauty part is this is the use of capacitor on a small scale. Let me show you the energy storage application. Here, this is a large scale. We have a big capacitor. What it is, this is a very high voltage supply. It goes up to about 2,000 volts or more. We won't go that high. What I have here is a meter across the terminals of this, which is also, the voltage also goes on to these things, which are uncharged, thank God, right, because I touched it. And what we're going to do is charge. This is a very large capacitor. And we're going to, you'll see the voltage go up. It'll give you a feeling for how slowly, with a very large capacitor, it charges. Okay, so now it's charging. We can get up to 2,000 volts at this, but it's slow. People in the front row can maybe see that. And as I was saying, no, it's going to take a while. All right, So the point is that in there, charge is slowly coming out of the power supply, going onto plates or inside of this thing. The high voltage thing means that high voltage will appear, of course, but you can imagine if the voltage gets high enough, it could make a spark. So these are specially designed capacitors. Now, to protect the instructor, we have earphones, but I'm not going to let it go up too loud. Maybe up to about 1,000. And what I'm going to do is, okay, that's enough. I'm going to turn this off because I'm instructed to do that so that I don't short out the power supply. So now this is off, but see the voltage is stored. The voltage is still on, even though that's off, because this thing is charged up. So that's that situation there. And now, maybe you want to cover your ears. I kid you not. Okay. Even I can hear that with these great things on. So, all right, that's that. Okay, well, let me point out to you that that's fun and games, but in real life, there's a very serious use of that. Oh, well, one of them is in your flash in your camera. Because you wonder, I put in like a 1.5 volt battery, and it can flash a lamp. Now, flash a lamp needs a big charge, big voltage, to jump across and make a spark in your flash lamp. How do they do that? Well, they have some circuitry here which boosts this 1.5 volts, and then they store it on a main capacitor. And then when you go click, it discharges that capacitor into the lamp, and you get your flash. Okay, so you use that regularly. And then this one is really the big deal. At Livermore, there is the Lawrence Livermore National Lab, named after Lawrence professor here, who had, I think, nothing to do with that lab particularly, but anyhow, they named it after him because he's a great man. And there, what they're doing is they have these kinds of capacitors in spades. They have rooms full of these capacitors. And here's the story on it. They have 12,500 square foot capacitor bays looking like that, which they charge up to 400 million joules of energy. The idea is they're going to have flash lamps around lasers. So what they're trying to do is laser fusion. They're trying to get an enormous bunch of laser light to come down on a pellet the size of, I think it's like the head of a pin, more or less. They have 96 beams coming in. So they start out with one little laser pulse. They put it through these amplifiers, which are flashed by these flash lamps. So they have to fire all the flash lamps at once within a few hundred microseconds, dump all that energy into the flash lamps, boost up this pulse, and then try to crush hydrogen into helium. So what they point out is that these banks of capacitors, when you release it, they have 100 million amps of current comes out of them. The peak power is 1 trillion watts, which at that moment is using more power, energy per unit time, than the whole United States. They do maybe a couple of shots a day because they're charging up the capacitors and they're tuning everything up. So in fact, if you want to go and see this, you can go to see it. You just have to ask permission and get approval, but you can go and visit this lab and see. They'll give you a guided tour. But this is capacitors. It must be the biggest set of capacitors in one place in the universe, I would guess, and I won't be proven wrong. So what they do there is they charge up these capacitors, they zap them into flash lamps, they boost the laser power until they hope to get fusion. And so that's the use of those things. Are we up time? Yes. Okay. Well, we'll do magnetism on Monday.